Yeah, now it has started. Yeah, thanks for reminding me. Okay, so we are given this set of vertices. There are these 8 vertices and I think 6 plus 6, 12 edges. Okay. And let's say I ask you, is there a vertex cover in this graph of size at most, let's say 5. Okay. So our goal is not to solve this problem. This is in general a hard problem. Okay. This is an NP complete problem, vertex cover. And instead, we want to reduce it to some other problem, dominating set. Okay. So notice that size of dominating set can be much smaller than the size of vertex cover. Right. So what is vertex cover in this graph? You have to pick 2 among ABC, 2 among uh, DEF, and 2 among FGH. Right? Otherwise, there will be some edge which will not be covered. For instance, I pick just F here, then G, H will not be covered. Okay. So vertex cover is in general, it is at least 6, it seems, this graph, or can we have 5? Maybe that's 5. So what is a vertex cover in this graph? A, B, then what do we pick? A, B, E, F, no, E, G. Okay, so anyways, that is not important. Let's say we want to ask this question, is there a vertex cover of size at most 5? Okay, so our goal is not to solve this question. Okay? Instead, we want to give a reduction to dominating set. So we want to say that if I can solve dominating set on a particular graph, then I can give you the answer to this. What is the size of the vertex cover in this graph? Okay. And there was one idea we were discussing, which was that convert each edge into a triangle. Okay. So all these edges, A comma B, B comma C, A comma C, instead of that we will have a triangle. Nice reduction. So for every edge U comma B, we'll introduce a new vertex UV and connect it with both U and B. Okay. So instead of just a single edge, we will now have a triangle. So we have these 3 vertices, all of which are connected to each other. Okay. So for every edge, we are introducing this new vertex UV and connecting it with both ends of the edge. Okay. And this we do for every edge. Now the question is, if I can find dominating set in this graph G prime, then how am I sure that I will get a vertex cover in the original graph? Okay. So notice that we are neither giving an algorithm for vertex cover nor for a dominating set. We are not describing any procedure. We are just saying that if you can find a solution to the dominating set, you can also find a solution to vertex cover in the original graph. Okay. So notice that both these problems are in fact NP complete. okay, as we will see later. And so how to prove NP completeness is that you start with some NP complete problem and give a polynomial time reduction from that NP complete problem to our problem. Okay. So if our problem was easy, then we could have solved that NP complete problem easily. So therefore our problem should be hard. Okay. So whenever you want to show that the problem is NP complete, you just pick some other NP complete problem and give a polynomial time reduction to the problem you are interested. Okay. Now we want to formally prove that if I can find dominating set in this graph G prime, then I will also have a vertex cover in the original. Okay. So I'll show you how to prove these things, and then you can try a couple of examples on your own. Okay. So this is what we are claiming is that G has a vertex cover of size K if and only if G prime has a dominating set of size. Okay, so we have to prove both directions. So what's happening here is we want to show that if G has a vertex cover of size K, then G prime has a dominating set of size. Okay, so that means that at least one dominating set will have the same size as that of the vertex cover, right? And what we also want to show is the other direction, that if I can find the dominating set of size K, I can also get a vertex cover of that size. Okay. So both directions we will have to show, and that's what we'll do now. Okay. So let's look at the first direction. So what is it that we want to show? That let's assume that G has some vertex cover of size K, then G prime will have a dominating set of size K. Right? So we assume that G has vertex cover of size K. Every edge in G will have one of the vertices belonging to the vertex cover. Right? This is just a definition of vertex cover. I don't know what has happened. Let me hit this. Okay. Yeah, it's fine. Okay, so now we just apply the definition. Okay, yeah, we know that G has a vertex cover of size K. Therefore, every edge in G has one of the vertices belonging to the vertex cover. Right? So for every edge E, so there is an edge E from these two vertices U to V, at least either U or V will be a part of the vertex cover. Right? So now, how do we proceed? Okay. So if U is contained in the vertex cover, then the adjacent vertex is V, right? So it is also covered by some of the elements in the vertex cover. We just go to this. Okay, yeah, now it's moving properly. Okay, so U is contained in the vertex cover, then the adjacent vertex V is also covered by some of the elements in the vertex cover. Right? That is just, we are just using the definition of vertex cover so far. Somehow we want to get to the dominating set part. So now for all the newly added vertices, UV for each edge. So remember the construction of this graph G prime, right? So we had a newly added, so we converted each edge into a triangle And for every edge u comma v, we brought this new vertex uv, right? So this vertex is adjacent to both u and v, one of which is at least a part of the vertex cover. So here we are using the fact that for every edge, at least one of the vertices will be a part of the vertex cover. Right? And what we want to show here is that whatever the vertices are there in this vertex cover, that will be a dominating set for the new graph G prime. Right? So how are we going to prove that? So whatever the old vertices are there, they are anyways covered because of the definition of the vertex cover. The only thing is this new word, newly added vertices. Okay. So these newly added vertices are adjacent to both endpoints of the edge. Right. That is how we create that triangle U and V. And at least one of them is a part of the vertex cover, and hence it is also part of our dominating set. So the additional vertices for all the edges, they will also be covered by this vertex cover. Right? And hence the set of vertices which form the vertex cover of size k, they will also form a dominating set in a new graph G prime. Okay, so this is a very straightforward proof. And so every vertex cover of size k will also be a dominating set in our graph. Okay. Now we want to prove the other direction, which is dominating set in this new graph will correspond to some vertex cover in the original graph. In fact, not just a vertex cover, it is a small vertex cover. Okay. So this is what we have. If G as a vertex cover, G prime as a dominating set of the same size. Now let's go to the other direction. Let's assume that this graph G prime has a dominating set of size k. Now, how should we prove this? How will it correspond to vertex cover of size k or smaller? Yeah, any ideas? Can we show it by removing newly added edges? Yeah, that's exactly the idea. Okay, so I think you can see it. So let's see how the proof goes. Uh, so two possibilities are there. Either the vertex in the dominating set is an original vertex or it belongs to a newly added vertex. This newly added vertex was the triangle. Okay. Okay. Right. Yeah. And what's the second case? Is that it belongs to the newly added vertex. It's UV for every edge U comma V. Okay. Now what do we know about this newly added vertex is that every new vertex is connected to the two vertices of this edge. So you can replace it by either of those two vertices and still whatever vertices were covered by this new vertex, they will still remain covered and possibly some new vertices. Okay. So since these three vertices form a triangle, so even by substituting with either U or B, we can continue to span all the vertices that were spanned before replacing. Right? So whatever vertices were covered earlier, they will still remain to be covered. Okay, so this way you can eliminate all the newly added vertices and replace it with either of these endpoints of those edges, and this will lead to the elimination of all newly added vertices while we are still covering all the edges of the graph G prime. Okay. So now you have reduced the second case to the first case, that every vertex is an original vertex in the graph. Okay. So the newly added vertices, they are dominated by the modified dominating set, and they also cover all the edges in G with at least either U or B for each edge U comma. Right? So for every edge, we are including at least one of its endpoints, U comma V. And that is exactly the definition of vertex cover, right? So for every edge, you have at least one endpoint. You cannot have both endpoints of that edge not in the modified dominating set. And therefore, if you have G prime, which has a dominating set of size K, G will also have a vertex cover of size at most. So there is a question. What are the newly added vertices here? So what we were doing is that we were converting every edge to a triangle. Right? So G prime is not the original graph. G prime is the new graph which we have constructed. G is the original graph. Okay. So when we are converting every edge to a triangle, you have to bring in some new vertex and connect it to both the endpoints of that edge. So that is exactly the new vertex, right? So let me just go back to that definition. No, it was not here. Okay. Yeah, so we converted every edge to this triangle. For every edge UV, we introduced a new vertex UV, okay, and connected it with both U and V. Okay. So this is what the definition of this new vertex is. So hopefully it's clear. So for newly added vertices, this vertex is adjacent to both U and V, and one of which is at least a part of the vertex cover. Therefore, the additional vertices, they'll also be covered by this vertex cover. Okay, any other questions in this proof? Either direction? There is something more. Okay. No, G prime was not the original one. G prime is the new one. Okay, so this is one reduction we have done today. Now let's move on to another, which is difficult to prove, but once you get the idea, it is very easy in fact. So I'll give you some time to work out this particular thing. Uh, yeah, so now we want to show that vertex cover is NP complete. Okay, so how do we prove that something is NP complete? You start with some NP complete problem and give a polynomial time reduction from that problem to this problem. Okay. In fact, satisfiability was the first NP complete problem which was discovered, and once they had this first, they showed that many other problems are also NP complete. Okay. So this is some random three set. So you have all these clauses, no limitation on number of clauses, and there are only three variables per clause. Okay. Now you are given this instance of three set, and you want to reduce it to vertex cover in some graph. Okay. Uh, so some satisfying assignment to this three set instance should be a vertex cover in our graph. So yeah, how should we do this reduction? So what graph should we construct from this x, y bar L1? And what are the vertices of this graph, edges of this graph? Yeah, so we have an answer. Make a triangle from three vertices and connect two triangles of graph by common vertices between two triangles. Okay, so what are these triangles? I guess it is denoting a clause by a triangle. Then it's connecting. Okay, you are getting there, but this doesn't work. Partially correct, in fact. Because the problem in triangle is you have to pick two vertices to cover that triangle. Whereas what we are saying here is that even if only one of them is true, then the entire clause will become true. So somehow we want to capture that fact. Okay, so let me show you how we are going to do this. So we'll again draw a graph with vertices labeled by these variables. Okay. So what are the variables here? X, Y, L1, L2, L3, U, V, W, Z, and there will also be these complements. So X bar, Y bar, L1 bar, W bar, Z bar. So all these vertices will be there. And there will be a triangle for each clause, exactly as was suggested. And there is also an edge between. So this is what we call a clause gadget. Okay. So there is a triangle for each clause and an edge between variable and its complement. Okay. There will be an edge from x to x bar, y to y bar. There is also an edge between a variable and a triangle if that variable appears in that particular clause. Okay. So for instance, let me show you what this graph will look like for the first clause. Okay. We will have this triangle and these edges x to x bar, y to y bar, L1 to L1 bar, and there will be edges from x, y, not y, in fact y bar and L1 because these are the three things which are being uh, which are in this clause. So we'll draw a triangle between x, y bar and L1. Okay, so we don't name the triangle as such. We just draw edges from x, y bar, L1 to different vertices of that triangle. Okay, so you see the graph, I guess, and what we want to show is that let's say there are m variables and L clauses. Then there exists a vertex cover of size m plus 2l if and only if phi is satisfiable. So this is our original formula. So this formula is satisfiable if and only if there exists a vertex cover of this size. Okay. So what is vertex cover for this graph? Right. So you look at all the edges, which is x comma x bar, y comma y bar, L1 comma L1 bar, and then there are the edges going to various vertices of the triangles. Okay, so you have to cover all these edges. You want to find a subset of vertices which covers all these edges. So notice that at least one among x and x bar have to be covered, at least one among y and y bar have to be covered, and similarly at least one among L1 and L1 bar should be covered. So for every variable, we are including one of at least one of those. So there will be these m many vertices, okay, and for every clause we have this triangle, right? So for covering a triangle, you will have to pick two of those vertices in that vertex cover. Two of the vertices of the triangle in our vertex cover. So for every clause, you will have to pick two vertices. Okay? And so we want to show that there exists a vertex cover of size m plus 2l if and only if phi is satisfied. So again, we have to prove two things. If there is some satisfied assignment to this x, y, z, x is true, y is false, and so on, then you can always find the vertex cover of this size, m plus 2l. And similarly, if you can find the vertex cover of this size, then that will give you a satisfying assignment for this formula phi. Yeah. So how should we prove this? Any ideas? First, maybe let's look at this direction. If there is a satisfying assignment for P, then there exists a vertex cover of size m plus 2l. Okay, so let's see. From a satisfying assignment, we want to give a vertex cover of this size. Okay. So suppose we have a satisfying assignment for phi, and for each variable to add the node corresponding to the true version of the literal for that variable to the vertex cover. Right? So in this case, let's say x was true, then we will add x to the vertex. Or if y bar is true, then we will add y bar to the vertex curve. Okay. And then for each clause, we select one true literal in the clause and add the remaining true literals to the vertex cover. Okay. So what is happening here is that there will be all these edges from x, y bar and L1 to different vertices of the triangle. Okay. And whichever is true, we don't pick that vertex. Okay. So whichever are not, which are not set to true, those vertices in the triangle, we will add in our vertex cover. Okay. So there are two vertices we are adding per clause and one true variable. Okay. So the total size will still be m plus 2l. Okay. So we have used two vertices in each clause gadget. So let me just go back. So this clause gadget was this triangle. Right? So we have, and variable gadget was just this edge between a variable and its complement. So these are all part of the variable gadget. These are this triangle is part of a clause gadget. Okay, so we have used two vertices in each triangle, which was the clause gadget, and one vertex in each variable gadget for this cover, which meets the size requirement of the cover. Okay. So this is how we get this vertex cover, and what we want to now prove that in fact from a satisfying assignment for P, this is indeed a vertex cover. Okay. So each edge in the variable gadget, which was just an edge between a variable and its complement, it is covered by the node selected from that gadget. Right. So we selected one true literal in this clause. And so each edge in that variable gadget will be uh, covered by this node, right? So for each of these variables, one of them has to be true. Either x or x bar has to be true, y or y bar has to be true, or L1 or L1 bar has to be. Okay? So each edge in this variable gadget will be covered by the true node, and we have these triangles for each clause. So all three edges will be covered by the two nodes which were selected in that clause gadget. Okay. So the triangles are covered, the variable gadget is covered. Now the only thing is these edges which are going from uh, triangle to variable. Okay. So one true literal in each clause is left out of the cover. Okay. But because it is a true literal, it is connected by an edge to the node corresponding to the true literal. So let me just show you this. So we had these edges from x, y, L1 bar to different vertices of that triangle. Okay. So whichever is true among these x, y bar and L1, that we will cover using these edges. Okay. Which edge going from that particular variable to this particular triangle. Okay. And the other two, we will include other two vertices of the triangle, we will include in our vertex cover. So the triangles are covered, the variable gadget is covered, which is just an edge between variable and its complement. And these edges which are going from a variable and the triangle, that is also covered. Right? So all three edges in the clause are covered by the two nodes we selected in that clause gadget. And one true literal in each clause gadget is left out of the cover, but because it is a true literal, it will be connected by an edge to the node corresponding to a true literal in a variable clause. Okay? Therefore, these nodes cover all the edges in the graph and we have a valid vertex cover. So any questions in this proof? Okay, so I guess the proof is clear to everyone. Now the other direction which we want is that if I can find a vertex cover in that graph, then I can also get a satisfying assignment for P. Okay. So if I have a vertex cover of size k for this graph, then what should I have? So variable gadget is just an edge from x to x bar for every variable. So at least one of those nodes have to be there, and two nodes have to be there in the triangles, right? So which is just a clause gadget to cover the edges in those gadgets. So totally we will need m plus 2l, where m is the number of variables and l is the number of clauses. Now from the vertex cover, I want to give a satisfying assignment for. So we take the literal corresponding to a covered node in the variable gadget to be true. Then this assignment will always satisfy phi. Right? So variable gadget was just edge from x to x bar, y to y bar, all these kind of edges. And we look at our vertex cover. Okay? And let's say I picked x in my vertex cover, then I will set x to be true. Okay. So now why will this satisfy phi is that for each clause gadget, which was the triangles, each of the three edges connecting the clause gadget to the variable gadget, that will be covered. Correct? And only two nodes in the clause gadget that are in the cover. Right? So we don't have to worry about the triangles, and because what this assignment will do is that only one literal is being set to true. Okay. But then we are picking those two other variables in the clause gadget so that the triangles are covered. So don't worry about the covering part. It's just that we are picking the literal corresponding to a covered node in the variable gadget, and that is it. Okay. So one of the clause gadget edges, triangles, must be covered by a node in the variable gadget. And so the assignment of that covered variable gadget literal will be set to true in C. Okay. Okay. So this holds for every clause gadget and clause. So this assignment will always satisfy phi. So k vertex cover of this graph will correspond to a satisfying assignment for phi, and a satisfying assignment for phi will also correspond to a k covering of this graph. Okay. So both these things we need to show, and therefore this reduction is absolutely fine. Okay, so we have some more reductions to cover now. Now we want to show vertex cover in polynomial time. Okay, there is a question. If a node here refers to the vertex in the graph, yes, node here refers to the vertex in the graph. So node means it is a vertex of that way. Yeah, node and vertex, they are the same thing. So okay. So we'll see one more reduction, which is vertex cover in polynomial time reduces to clique. So vertex cover is just subset of vertices that cover all the edges, and clique is subset of vertices that are all directly connected with an edge. So we want to pick a subset of vertices such that any pair of vertices, if you pick, there must be an edge between them. Okay? So this is a very nice reduction, which is you are given a graph G, V, comma, E and integer K, and you want to ask the question, does this graph have a vertex cover of size at most K? So then we will generate this complement graph. Actually, this should be G prime, which is V comma E bar. Okay, so the same set of vertices, but whatever edges were not there in G, we will include it in G prime. Okay, so it's just the opposite of that. And then we ask the question whether this new graph G prime has a clique of size mod B minus K. If there is a solution, return yes, else return no. So why should this thing work? Okay. So the two things we need to show is that if there is a solution to vertex cover G comma K, then there must be a solution to clique G comma V minus K. Right? If there is a vertex cover in the original graph uh, of size K, then there must be a clique of size V minus K in the modified. And similarly, we'll also want to show that if there is a solution to clique G comma V minus K, then there must be a solution to vertex cover G comma K. So we'll prove the first thing, which is we'll suppose G as a vertex cover of size K. Then just use the definition, which is that for all adjacent vertices, at least one of them should be contained in our vertex cover. Now we just take the contrapositive of this statement, which is that if both of these are not there in our vertex cover, then there cannot be an edge between those two edges. Right? So that means this will be an edge in the complement graph. Okay, so this is called a complement graph, where whatever edges were not there in our original graph, we are including in the new graph. Whatever edges are there, we are not including in this new graph. Okay. So now what does this say is that any pair of vertices that are both not in this vertex cover V prime, there is an edge between them in this new graph. Okay, and that's exactly the definition of clique. Okay, so the union of all pairs of vertices that are all not in V prime, simply V minus V prime. Okay, and hence V minus V prime is a cliquing G because there is an edge between all such vertices. Thus, V minus V prime will be a cliquing G. Okay, so this was one direction where you transform the solution to the vertex cover problem to get a solution to the clique problem. Now we want to prove the other direction. Suppose that this graph G has a clique V prime with this size, right? So let U comma V be an edge in E bar, then U comma V does not belong to E, right? That's our definition here, and which implies that at least one of U or V does not belong to this vertex cover. Not vertex cover, sorry, clique. Okay. So because the definition of clique was that any two vertices must have an edge between them. Okay, so any two vertices in V prime must have an edge between them. Because we are picking this U comma V which is not in E, that means at least one of U or V does not belong to V prime. Okay. And therefore at least one of U or V is in V minus V prime. And this will cause the edge U comma V to be covered by V minus V prime. Okay. So this was any arbitrary edge. Okay. So every edge in E will be covered by this particular set V minus V prime. So because we didn't choose anything, right? So this could be any edge in E prime or E bar in fact. And that's the way we'll show that V minus V prime, this will be a vertex cover G with size K. Okay, so both the directions are done. Any questions? Sorry, there was a question. Yeah, we have a question. Uh, yeah, we chose it arbitrarily. So from the complement of the set of edges. Okay. This contradicts point 4 of the proof. Oh, sorry. So this should be E prime. Yeah, that is a typo. Thanks. So every edge in E will be covered by this remaining set, right? Because what this click was doing, it was covering, yeah, those edges which were not there. And okay, so yeah, so if there is no more questions, yes, we are done with this class. Okay. So next week is Diwali break, and we'll meet after uh, the next week. Okay. So happy Diwali to all of you. Is there a question?
Happy Diwali, sir.
Yeah.
Thank you, sir.